Hello everybody, and welcome to our next session and lecture. Today we're going to be having a short review of the principles behind plate tectonics. Now before we begin, I wanted to take 1 second just to talk about the importance of questions and learning. One of the forward educators and naturalists and scientists right now, his name is John Mirabaz, and he shared this really great quote that I wanted to begin our session with, talking about questions. And John Mirabaz says, "We are born into curiosity, a quality that can either be developed or degraded by experience, and can always be enhanced by practice. Think of curiosity as a skill that you can improve over time. You can train yourself to find rich questions hiding everywhere. And the finding of questions to ask and drive our learning is really what's at the center of studying physical geography and its earth science theory. And so those importance of questions are why we started this week with our Zoom asking, what do we wonder about tectonic processes? And you all came up with some phenomenal questions. The first being, we wonder why earthquakes don't happen everywhere with the same magnitude. And we wonder why there are more faults in the eastern region of Bhutan. And we wonder why different regions of our country are categorized into different tectonic and earthquake zones. And so these questions are going to drive the lectures over our next 2 sessions. And to start off with, we wanted to tackle this first one. Why don't earthquakes happen everywhere with the same magnitude? You noticed this pattern here in Bhutan. But to truly understand this question and seek our answers, we have to expand from a local to a more global understanding. And when we do so, when we look at the distributions of earthquakes worldwide, we can see that the same question still applies. Why don't earthquakes occur everywhere, and why do earthquakes occur in different locations with different magnitudes? And we can see that just as within Bhutan, we can notice some patterns, right? That earthquakes occur in specific locations, including the middle of oceans and along the belts in some places where oceans meet continents, but in not all cases where ocean meets continents. And so this distribution of earthquakes and understanding these patterns leads us to one of the largest revelations and understandings for earth science and physical geography in the past 50 years, and that is the phenomenon of plate tectonics. Plate tectonics really is that manifestation of the different earthquake zones. These plates match and line up with those earthquake patterns that we're witnessing. And plate tectonics, to provide you a definition, is the matter in which Earth's lithosphere moves around. So to understand plate tectonics, we have to break down those terms a little bit, particularly this word, lithosphere. So let's jump in. If we were to take a cross-section of the Earth, we'd notice that it forms into a few different layers. The top portion being the crust, the large majority of the Earth being made up into the mantle, and then 2 sections of a core, a liquid outer core and a solid inner core. This topmost section of the crust and the upper mantle is what is known as the lithosphere. And it's made up of the brittle sections, the solid, the rigid sections of these portions of the Earth's crust. So the lithosphere is the coolest and most rigid part of the Earth's surface. But to understand how the lithosphere moves around and interacts on the Earth, we have to take a bit of a deeper dive into its individual components. Because we can see that although the lithosphere is both the crust and this upper part of the mantle, not all of the crust is made equal, right? In some places beneath the oceans, we have a thin crust, and beneath the continents, it seems the crust is thicker. And so to understand this distribution, we can look at a really important tool called a hypsometric curve. So it's a graph that shows the relative elevation and the percent of land of the Earth's surface that is at that elevation. And so this graph might look complicated when it has all these labels, but if we were to remove those differences, we can see it's actually quite simple. That the pattern, it almost looks like there's a stair step going in two large platforms. And so the way to interpret this graph is it shows us that the highest peaks on Earth and the lowest peaks on Earth really make up just a small percentage of the total amount of Earth's surface. And instead, the majority of our land is bounded in between these two elevations, really between 2 kilometers and 0 kilometers above sea level right here, and then straddling between 4 to 5 kilometers down here. And this distribution really helps us see the nature of both the ocean floor as well as the continental interiors. The reason for this distribution comes down to the nature of the crust, which makes up these two types of landforms. If we look at oceanic crust, it's made up of a material primarily known as basalt, a rock that's basalt, which is usually, it's younger, it's thinner, but it's very dense, very heavy. And so it rests around this 4 to 5 kilometer region. As opposed to continental crust, made up of primarily granite. And oftentimes these continents are older and thicker. However, their main material is less dense, and that it can rise to this average elevation. And so density and the difference in density between these two types of crust is really what's going to determine our interactions between plates. And if we were to look a bit further into this to understand how these two types of crust will interact, we can look towards the driver of plate tectonics. And again, taking a cross-section of the Earth, we can see that the interior of the Earth is actually mobile. It's fluid. And we describe this process known as mantle convection. And this is mantle convection that drives the movement of oceanic and continental plates. As this mantle moves, it provides a motion for these plates to interact. And where the mantle wells up, we see that plates are splitting apart. And where the mantle forces two plates together, we see that there's interactions occurring. And so these interactions are what's known as boundaries between plates. And understanding these boundaries is key to understanding earthquake occurrence and distribution. So let's take a look at these boundaries in a little bit more detail. Three main types of boundaries that we'll look into are divergent, constructive, and we have conservative plate boundaries, where plates will slide past each other, and then we have convergent, or destructive, right here. And so let's break them down. A constructive plate boundary is where plates diverge and new crust is produced. One of the easiest places to see this is within the ocean floor and looking at the seafloor spreading centers. If I take this pen off, we can see in these animations some really steady flow. As the mantle wells up, the continental crust is diverged and creates this constructive boundary where new crust is formed. Constructive plate boundaries aren't only limited to ocean floors, however, they also happen on land, where if we have mantle upwelling beneath continents, it will provide these extensional forces to build new crust on the interiors. These constructive plate boundaries really lead us into our next type of boundary, which is a conservative plate boundary. This is where plates will slide past each other. We can look towards these ocean spreading centers, again to provide evidence, and particularly in breaks between those spreading centers. So if we look back to our model, our demonstration, we can see that while the main divergence is happening right here, we also have zones where we have splits, where there's sliding going on. So that sliding is our real conservative plate boundary. And this is earthquakes will happen right here, because these things, they stick and they slip, producing those seismic forces. And again, just like our previous example, conservative plate boundaries also happen in continental settings as well. And in these instances, two portions of the continental plate will slide past each other, producing earthquakes. However, the last thing we need to look at is what's known as these destructive plate boundaries, where two plates can converge and then crust is being recycled. Particularly when an oceanic plate, edge of a plate will meet a continental plate, it performs a process that's known as subduction, where the denser ocean material, oceanic crustal material, will actually dip below and descend beneath this continental plate, forming this subduction system. And that density, again, is really key in between. However, these destructive plate boundaries, this convergence, does not only happen in oceanic settings, but it can also happen within continental settings. And it's here where we can find some of the largest mountains being built. So this process is usually as follows. First, we have subduction proceeding normally, with ocean crust descending beneath continental crust, followed by these continental plates meeting and colliding. And then both edges will begin to buckle, then producing mountains and faults where the crust can increase in its thickness. So with these three types of boundaries, we can return to our Group 1's questions. We wonder why earthquakes don't happen everywhere with the same magnitude. And if we look at this distribution of earthquakes, it really aligns with our distribution of boundaries. We can see there are some earthquakes at these constructive boundaries. However, the majority of earthquakes are happening along our destructive boundaries, especially where one plate is subducting beneath another one. And talking about these forms of subduction, where the largest earthquake occurs, we can map them out looking at what's known as subduction earthquakes, or subduction megathrust earthquakes. And a megathrust earthquake is a large earthquake that occurs at these convergent plate boundaries. And we can see that these earthquakes, they are dependent upon local characteristics. So megathrust earthquakes don't only occur within subduction zones, but they occur anywhere and in some key places where where we have continental convergence as well. And so for our purpose, understanding distribution of earthquakes in the Himalaya, we have to understand this megathrust system. It's actually known as the Himalayan megathrust fault system. And so the take-home message from this lecture is really that these variations in tectonic forces and crustal conditions cause the variations in our earthquake. It's the different forces which are happening. But to understand this Himalayan megathrust system, and to understand the distribution of earthquakes in the Himalaya, we really have to understand the story of these mountains, how these mountains were built. So that is going to be the focus of our next lecture, where we continue to dive into your questions. Look forward to talking to you then.